Good morning, and welcome to the fifth annual Virtual Harmful Algal Bloom Research Symposium. The Algal Bloom Action Team is thrilled to be hosting this event for the fifth year, and we are glad you can join us. This year's symposium is organized into three sessions. This morning's session will have five presentations and will focus on harmful algal bloom prediction, prevention, and treatment. Then we will break for lunch. This afternoon, we'll have two sessions, two presentations on the human dimensions of harmful algal blooms, and then five presentations on HAB monitoring and detection. This session will run from 9 a.m. Central to 11:45, with a 15-minute break between at 10:30 a.m. Central. Of course, that's beginning at 10 a.m. Eastern, where I happen to be, through 12:45 Eastern. My name's Eugene Bregg, and I'm Program Director for Aquatic Ecosystem Extension with The Ohio State University. Each session will be moderated by another member of the Algal Bloom Action Team, a collaboration of water professionals, researchers, and educators from 12 states in the north central region of the United States. Team members include the National Network of Water Resources Research Institutes, the North Central Region Water Network, and University Extension within each state in the North Central region. In addition to hosting this annual symposium, our team has developed a website of resources that can be used freely for outreach and education around harmful algal blooms in the North Central region. And I really encourage each of you to visit that website. That is northcentralwater.org/HABs. Again, northcentralwater.org/HABs, which we're putting in the chat now. There you can explore some of the resources we have to date, including What You Should Know fact sheet, a fact sheet on preventing and treating harmful algal blooms for landowners, a fact sheet focusing on HABs and their health-related effects on animals, and a frequently asked questions page related to HABs. In addition to this symposium, we also host a bi-monthly, pardon me, we also host a bi-monthly webinar series where we feature the latest harmful algal bloom research all year round. On our website, you can find recordings of all our past webinars, information on upcoming webinars, as well as access information and recordings on our past HAB research symposia. Before we get started, a few housekeeping items. Each presenter is allotted a half hour, roughly 20 minutes for the presentation, followed by about 10 minutes for questions and answers. We will allow time for Q&A after each presentation. To have your questions addressed during this time, please post them in the Q&A panel, which can be located in your Zoom toolbar, ordinarily at the bottom of the screen. So again, post those questions to the Q&A panel. If there's a question already posted to the Q&A panel and you have the same or a very similar question, use the Zoom upvote function on the similar question, and we will prioritize those questions that are most upvoted. Please note the Q&A panel function is separate from the chat function in Zoom. Again, questions for presenters should be posted to the Q&A panel. If you're having any technical difficulties during the symposium, please let us know via Zoom's chat function, and we will be happy to assist you as best we can. You can also use the chat function to introduce yourself or discuss the research findings with fellow water professionals at the symposium today. Please note we will stick to time, so we will have to cut questions off when we reach the end of the allotted time for that presenter. That said, please put your questions in the Q&A panels, as presenters will try their best to answer remaining questions in written form as time allows. Following this morning's session, we will break for lunch and resume at 12:30 p.m. for session 2. All symposium presentations are being recorded and will be posted to the Algal Bloom Action Team website at the conclusion of the event. We will also post the presentation slides to this website for your reference. So let's jump right in. I'd like to introduce Dr. Caitlin Reinl, research coordinator for Lake Superior National Estuarine Research Reserve. She's a limnologist with a broad focus on how the synergistic effects of climate and watershed influence impact inland water quality. And you can read the rest. Tremendous work in freshwater systems. We're very glad to have Kate with us. Please carry on. Welcome, Kate.
Thanks. Good morning, everybody. I cannot believe what a huge number of people are joining this morning. So let me share my screen real quick here. We practice this, but you never know how it's going to go. Alrighty. Are you guys getting the right thing?
It looks good. Thank you.
Excellent. Thank you. So again, good morning, everybody. It's really great to see so many people are joining and likely from a lot of places beyond the region that I'm working in. So thank you again. We're going to ease into things this morning. I'm not going to hit you with a super technical, overly complicated presentation because I'm sure some of you are having your coffee for the first time right now as you're watching this. So today I'm going to be talking about blooms in Lake Superior. You may have seen some of this work in the past, but this is going to be on a new published data set that myself and Brenda LaFrancois put on EDI last year, I believe, with a little bit of where we're at with our knowledge of what has been causing blooms in this in the Big Lake. For those who might not be familiar, the Lake Superior National Estuarine Research Reserve is a network of 30 reserves around the country that represent a partnership between NOAA and the states, where NOAA provides kind of our marching orders and our guidance, and the states carry out the day-to-day activities. All of these reserves are dedicated to research, education, outreach, and stewardship. We are located here in Superior, Wisconsin, just across the bridge from Duluth, Minnesota, and there will be another one coming online in our region soon in Green Bay. So I just want to zoom out for a minute here. So we talk about freshwater, many of us just like in our daily lives and we don't think about this kind of from like this zoomed out global scale. So I want to if take a moment and really kind of think about this from the macro scale. So 71% of Earth's surface is covered by liquid fresh water. If you were to condense all of this water down into a sphere, the water that's on top, in, and under the Earth surface, and you were to compare that a sphere to the Earth sphere, and this is a graphic from USGS, this is what it would look like. So when we look at these, photos from space of Earth, it seems like, wow, this is a place that's just completely covered in water. But when you take it and you put it relative to the Earth size, it really doesn't look like so much. Then you drill down further and you have Earth's fresh liquid water. So most of the water on Earth, as many of you know, is actually salt water. It's not water that we can easily use. But even then, a lot of that fresh liquid water is actually frozen or it's not actually like immediately accessible. It's in glaciers and other things. And so the fresh liquid surface water, when you condense it down into a sphere that's available relative to the Earth, looks like this. And I think that this is just like a really compelling graphic to understand the importance of the work that we're doing here and the importance of our freshwater resources. And I'm going to show this in a couple of different ways for just to really kind of nail this point home. I know that many of us really understand and value the importance of freshwater, but I think taking the time to really understand that it's not as abundant as we often think is really important. Lake Superior, which I'll be talking about today, holds 10% of Earth's fresh liquid surface water. So of that very tiny pin that you're seeing on the Earth right there, 10% of that is contained just in Lake Superior. Another way to look at this, and this is another really nice graphic from USGS, is that this is the total global water, and 96% and some change is ocean water, and only 2.5% of that is freshwater. Of that freshwater, only 1.2% of that is surface freshwater. And of that 1.2% of that 2.5% water, 20.9% of that is in lakes, and another basically 0.5% is held in rivers. So that's again demonstrating it's really a very small fraction of the total water on Earth is actually available to us and the other beings that live on this Earth to access, to live and survive. So Lake Superior holds 10% of that water. It's the largest lake in the world by surface area. It's the third largest lake in the world by volume. Lake Baikal and Lake Tanganyika are up there as well. And then the other Laurentian Great Lakes contribute another 10% of the Earth's water. So the Laurentian Great Lakes, meaning Lake Michigan, Lake Huron, Lake Ontario, Lake Erie, and Lake Superior combined hold 20% of the entire Earth's fresh liquid surface water, Lake Superior holding half of that water. And because of that, Lake Superior has importance all the way from the local scale up to the global scale. So at the local scale, people here where I live and work are spending time recreating on the water, using it for cultural purposes, using it for sustenance, going fishing, and things of that nature. And on a global scale, when you say the word Lake Superior, almost anywhere that you go in the world, people know what you're talking about. It has a reputation in the world. And the even more important thing is that Lake Superior often has a really good reputation as being this immaculate, pristine, unbelievable freshwater resource that truly draws people in from around the world. And so, from the local level and to the global level and everywhere in between, Lake Superior truly is an important and critical freshwater resource. So, as I said, Lake Superior is one of the five Laurentian Great Lakes. If you're not familiar, it's up here where we have Lake Michigan, Lake Huron, Lake Erie, and Lake Ontario over here. So these lakes, although they're part of one system, are actually really diverse. So they have a really huge biochemical gradient or really extraordinary biochemical gradient where Lake Superior is considered oligotrophic or low nutrient. And then as we move down into the lower Laurentian Great Lakes, they become more eutrophic. And because of this range that we see in nutrient conditions as well as other biophysical and chemical conditions across the Great Lakes, we have a really wide gradient in water quality characteristics. So, Lake Erie, unfortunately, often has the reputation for having really terrible algal blooms that are occurring every year and are really expansive across the lake. And specifically, they're having harmful algal blooms caused by cyanobacteria or toxic cyanobacteria. Whereas when we think of Lake Superior, we often think of this. So it has this reputation as being beautiful, pristine, clear, drawing tourists just to spend time and get to, really bear witness to these beautiful waters that we have here. And by many assessments, Lake Superior is in great condition and things are not changing. So this is a draft for the 2025 State of the Great Lakes report that's showing the nutrients and algae status and trends for all of the Great Lakes. You'll see that Lake Superior here for all three metrics is noted as good and unchanging or good and undetermined. And be that as it may, we are still seeing things in our region that look like this. So Lake Superior has been experiencing cyanobacterial blooms, also known as blue-green algal blooms, for several years now. The first one that has been recorded in recent history, or to our knowledge, occurred in 2012 following an extreme storm event. And then we've continued to have these smaller sporadic events concentrated primarily in the western arm of Lake Superior. And this has been a huge surprise because it's really just something that we don't associate with Lake Superior. It's a low nutrient system. It's relatively cold. Anybody who's gone swimming in Lake Superior knows that when you jump in, it's kind of like you have to catch your breath, even at the height of summer. And so this is really surprising. And it's indicating to us that Lake Superior might indeed be going through some sort of ecological change. And so this has led to a lot of response and action, coordination and collaboration, which is really a success story in all of this among academics, tribal nations, and management from the state to the federal level. And so this is an example from the Cooperative Science and Monitoring Initiative coordination from the field year 2021. But these kinds of collaborations have continued and are trying to address and understand harmful algal blooms or cyanobacterial blooms in Lake Superior. One of the really big challenges that we find in Lake Superior is that because there are some areas with really, truly, pressing issues, and not that it's not pressing here, but I should say, really immediate health risks, such as in Lake Erie, the algal bloom issue in Lake Superior tends to be overlooked or downplayed. However, it seems that we are in a situation where there is ecological change that we need to kind of be aware of and be proactive about. And so this has really stimulated this coordinated, massive response from the community here. And one of the things that has come out of that is this data set. So this is a new data set that has been collected really in this kind of grassroots way called Lake Superior Cyanobacterial Bloom Reports 2012 to present. So when all of this started happening, Brenda LaFrancois at National Park Service located in Ashland, Wisconsin, started just kind of putting together a Google sheet and just writing down when these things happened and kind of all of the information around it. So it essentially started as kind of like a lab notebook. And we've continued to track these events, and this has turned into basically, or not basically, truly the only data set that we actually have on understanding and tracking these blooms in Lake Superior. And so for quite a few years, we were collecting this information and it was really kind of disorganized and sitting in a Google Drive, kind of just for the folks that were directly working on this issue. And very recently, we cleaned up that data set and we published it to make it publicly available for anybody who wants to see it or use it for research or other purposes in an effort to keep our research and data open, as well as provide an opportunity for researchers to work on this problem. So I'm going to give you a little bit of a flavor of what we have in this data set, and then I won't leave you hanging. I'll talk a little bit about what we think might be causing cyanobacterial blooms in Lake Superior as well. Okay, so just a little bit, one text-heavy slide, I promise, just to introduce this data set. So the purpose of this data set is important to really kind of define what this data set is even for, is to collect observations of blooms for Lake Superior and connecting waters to document patterns in their occurrence and provide insights into their causes. Otherwise, we really truly have no information on these blooms that we can use except for anecdotal kind of, yeah, we know they're happening there, but we don't know much else. For this data set, we define a cyanobacterial bloom as an aggregation of cyanobacterial biomass in some or all of the water column, which may lead to the occurrence of surface scums or subsurface maximums. So just because biomass is not fully contained on the surface doesn't mean that there's not a significant amount of biomass. So we include both like DCM or deep chlorophyll maximums or deep chlorophyll layers, as well as surface scums in this definition. This data set relies on observations, data, photographs, and insights from a wide range of agency staff, many of which are USGS, EPA, Fond du Lac, and Red Cliff tribes, the Lake Superior Reserve, and academic partners, with key input from participants from the Lake Superior Algal Bloom and Lake Superior Algal Bloom and Nutrient Subgroup Collaboration, which is a part of the Lake Superior Partnership, which is a partnership between the U.S. and Canada. And this data set only includes reported blooms and likely doesn't include all actual bloom events. And additionally, there might be more than one report for a single bloom event, depending on its size. So those are a few caveats, and all of this information is contained with this data set as well. So the way that we are collecting these observations is using the humble Google form that many of us know and love. So there's a Google form that's available, and we try to circulate it as widely as we can. And I can also share it in the chat as well. But essentially, we have a Google form where people can come to it and input information about blooms, including the location, the more of like a quantitative description of the location. Was it in the western arm? Was it in a river or an estuary? Is it in the near shore, etc., as well as information about species and toxins and other general comments. There's also places for uploading field photos and lab results, etc. We've been tracking bloom events and observations over time. So this is just one flavor of the information that you can get from this data set. So we track the number of events, individual events, as well as the number of observations. As I mentioned, sometimes we get multiple observations for a single event, and so that information is contained in this data set. We also included some information on the level of verification or our level of confidence in whether a bloom actually occurred. So we have 4 levels of verification that we include in this data set. So we have suspected based on field observations but unconfirmed otherwise, suspected based on field photos or expert observation but not otherwise verified, verified via basic microscopy of cyanodominance, or verified via microscopic enumeration of cyanobacteria and or the presence of cyanotoxins. And this was an effort with lots of agencies and kind of like pulling together commonalities in the way that they define blooms. And we wanted to make sure that we weren't just throwing out events that could be blooms, but we also wanted to make sure that we're communicating the level of certainty and whether a bloom event truly was a cyanobacterial bloom. So something you'll see here is that over time, there have been more bloom reports, and in some years, we have a lot or more bloom events, with the highest number of events that we've recorded in our data set being in 2020. You'll note the color between whether it's a suspected bloom event versus a verified bloom event. And then this line over here gives an indication of the number of bloom reports in that year. So in some years, we get more reports than the number of actual unique events, which speaks to this question that we often get of, are people just noticing it more, or is it actually more events? And so we really try to pull apart those two elements because that's a question that often comes up. We also have information available in there about what months blooms are occurring in. So what we're finding in Lake Superior is that blooms tend to occur in later summer, which is pretty typical for cyanobacterial blooms, but we're also seeing them sometimes earlier in the year. And I think a lot of it really ultimately it depends on when, whether there was ice cover in the previous year and what time setup starts or stratification starts in the lake and things really begin to warm up. We also have information about toxins in these blooms. So these are individual bloom events, not bloom reports. And we also have information, that qualitative information about the region that these occurred in. So was this an inland water body that's in the Lake Superior Basin? Was it a riverine and or estuarine environment? Or was it in the Lake Superior nearshore? In our data set, the majority of the events that have been reported or recorded are in the Lake Superior nearshore, but there's also quite a few that have occurred in riverine environments, specifically or more often in the St. Louis River estuary than not. And then in these two categories, there have been two events where we had toxins detected. That said, there are cases where toxins were not tested for, and things of that nature. So it's really kind of like you have to really kind of think about the information that's being collected here and the nuances that go into it when you're using this data set. And I want to just make sure that that's clear. I also want to mention that we define the shoreline or the nearshore environment in this data set as visible from shore or less than 5 kilometers from shoreline or less than 30 meters deep, which is consistent with a lot of agency definitions of the nearshore. We also have information on the species composition. So we have entry for the primary species as well as any secondary or additional cyanobacterial species and other phytoplankton that may have been present in the bloom. We're finding that Dilacospermum is the most common species that's being found in the blooms, especially in the Lake Superior nearshore environment. More often, the species is, or most often, we found that it's Dilacospermum lemmermanii, which is not exactly the species that I'm showing here, but I just thought this was a nice graphic to show what this looks like up close. But there are other species that are shown as well. And then you can also see that there is this pink category for unknown or not tested. So in some cases we don't know, and we have an area to include that information as well. Again, we're finding that Lake Superior nearshore environment has the most number of bloom observations as well as unique events. So in the previous slide, I showed the number of unique events. This is the number of actual reports. And the part of the reason that I showed this is that people may collect samples from different parts of the bloom. And so it can be interesting to see if the species composition at different areas is the same or if it's different. And that's why I chose to display it in this slightly different way. We also find that there's more diversity in the cyanobacterial dominance in the riverine and estuarine environment, which is an interesting finding that's coming out from this data set. We also have a bloom extent piece, and we developed this data set to be somewhat compatible with the Bloom Watch app. If you're familiar, that's put out by EPA. So they have categories in there for like surface water conditions and weather conditions in Bloom Watch, or excuse me, and spatial extent. And we tried to mirror those categories in this data set so that if somebody wants to take those data sets and bring them together, it would be easier to do those things. And so we have this larger than football field, car, tennis court to football field categories. And you can see there's really kind of a mixed bag. With large events occurring in many different years. We have a lot more information in this data set, and like I said, I just wanted to give you kind of like a flavor of what we have in there, but there's information on toxin type, so microcystin, saxitoxin, anatoxin, and other metabolites that may have been present in the testing, excuse me. Toxin concentrations themselves, secondary species, as I mentioned, wave and surface water conditions, water temperature, weather conditions, and a lot more. So this is a really rich data set, and again, I believe the only data set that we have on blooms in Lake Superior, especially that's been made public. We also use this data set to produce this two-pager that's used by both managers and the public to communicate about blooms. So we put out a Lake Superior Bloom Bulletin. We've been doing this for the last 2 years. So we have one covering the 2022 summer field season. This is the one from the 2023 summer field season, and we'll be putting out the 2024 summer field season one relatively soon. But this is a really nice graphic for sharing about blooms. That goes a little more than the surface, but provides some really great information for communicating about this issue and what our current knowledge is and kind of what happened in the last year. So we have kind of a summary page, which is the front page, and on the back side is the kind of the deep dive into the previous summer field season. So some of you are probably wondering, why are there algal blooms in Lake Superior? So a lot of this information has been presented previously, but I just wanted to kind of throw a few slides in just because I know that there are probably some folks who are just new to this topic. So one of the primary reasons that we're finding is that Lake Superior is actually warming really rapidly. Even though it's relatively cold when you go into it, the rate of warming is actually quite fast. even globally. It's one of the fastest warming lakes in the world by summer surface temperature. We're also finding that the growing season of the lake is getting longer, and that's a really important factor. So, in years that we're seeing blooms, whether they're small or large, we're finding that the number of degree days or the longer growing there or the number of days where it's above a certain temperature are getting longer. So we're getting a longer growing season, which is leading to more opportunity for growth for cyanobacteria. Unlike a lot of the other Great Lakes, we don't have a catchment that has, a lot of development or agriculture. It's mostly forested. That said, we have been having a lot of storm events. And even though we have a forested watershed, that doesn't mean that there's not nutrients coming in. And so, especially in these extreme storm event years, which are being pictured here, 2012, 2018, there was also one in 2016 that was kind of centered in the Ashland area. These are leading to huge amounts of sediment and nutrients coming into the lake. And these are also fueling blooms. We're finding that the years with these events are the years where we're having larger blooms. So, in other words, basically, climate events, temperature and rainfall currently seem to be the driving factor behind the emergence of blooms in Lake Superior. That said, what we know is far outweighed by what we don't know. We know that these longer, warmer summers are a factor. We know that these largest storm events are a factor. Some of my work and others have indicated that nutrients as well as biological material from the watershed might be playing an important role in these nearshore blooms. But there's just so much that we really don't understand, and a lot of room for growth and understanding this issue. So a few takeaways: cyanobacterial blooms are becoming an annual occurrence in Lake Superior, seemingly. This is the only data record we have for blooms in Lake Superior that's now publicly available, and we would really love to see it being used for a wide range of research questions. Data collection as well as synthesis is critical to addressing this issue. So it's not just the collection, but truly the synthesizing of the data sets with others. Collaboration, coordination, or continued, I should say, between many different partners is going to be key to addressing this issue. And foundational information is still needed to identify and implement effective management actions. So before I end here, I just want to put in a quick plug. There's a new special section that's currently online in the Journal of Great Lakes Research on Lake Superior current conditions, trends, and emerging threats. You can find that if you just go to the JGLR website. It'll be kind of officially published in February. And then with that, I'll just say that if you want access to all of these things, like I said, we're very committed to open research, open data, and so you can find all of these things. Probably the easiest things for most of you to do is just to Google search 2023 Bloom Bulletin. That's located on Mines at UW, and then Lake Superior Blooms EDI for the Bloom data set. As I said, the 2024 data set will be coming up. Data set updates and Bloom Bulletin will be coming up in May. So with that, I'd really like to thank you for your time, and I'll take any questions that you might have.
Great. Thanks so much, Kate. We only have a couple minutes now for questions. Um, the I'm going to read one from the chat first that can't be posted to the Q&A. And the rest you'll probably have to get to in written form if you have a few moments to write to the Q&A panel on Zoom.
Sure.
Okay, great. So, what is the definition of or the criteria used to determine cyanobacteria dominance?
So I think it's just 50%. So, if it's 50% or more of a sample, then we would denote it as cyanobacterial bloom.
So, functionally a majority by
Yeah, functionally.
by
And then
density.
yeah, and then I think for our Canadian partners, they also indicate that if there's presence of cyanotoxins is one of the ways that they flag bloom. So that's a piece of criteria that can be folded into the enumeration as well.
One question from the question and answer panel. I think this is probably the last one we'll get to. How much water is tied up in aquifers? And I assume that means fresh water.
That's a really good question. So when I was kind of like plunking around on the internet looking for this, USGS has some really excellent graphics on that. So I don't have an answer for you right now, but like if you just go online and Google USGS aquifer map, you can check out some really awesome visualizations on that information.
Great, thank you so much. And if you have a few moments, if you can get to the rest of the questions in writing, it would be appreciated. Thanks for your
Yeah, of
time, Kate.
course.
It was really enjoyable.
Thank you.
Um, I guess I have one more comment of my own. I'm surprised that I didn't see planktothrix in your figures because it's often prominent in colder systems.
Yes, that's really true, and that's one of the reasons that we point to this deep chlorophyll layer. A lot of colleagues that I work with in the Alps region, they have a lot of Planktothrix blooms. There are, there are data sets that look at deep chlorophyll layers in the Great Lakes, and Planktothrix is just not something that's really showing up.
Great. Thanks for your time. Moving along, I would like to introduce Dong Chen and Bin Chen. Dong is a professor in the Department of Civil and Mechanical Engineering at Purdue, Fort Wayne. He received his PhD in Civil and Environmental Engineering with a minor in Geological Science from OSU, my very own institution. Welcome home, Dong.
Yeah. Thank
Um,
you.
his research interest is water and wastewater chemistry, monitoring, treatment processes, and corrosion science, and is a registered professional engineer in the state of Ohio. Bin Chen is associate professor in Department of Electrical and Computer Engineering at Purdue University, Fort Wayne. He received his PhD in biomedical engineering from Duke in 2008, and his research interest is computer science, including machine learning, data analysis, and imaging processes. So, welcome, Dong and Bin. Take it away, please.
Okay, thank you. Let me share my slide. Share. Okay, and slideshow.
So we are seeing your presentation mode.
Okay, it's did you see which screen? I'm not sure. Which screen are you?
I'm seeing using AI to predict. I'm seeing what looks like a title screen, but it is your presentation mode with your notes present in the sidebar.
Oh, okay. Okay, let me swap. Okay.
There you go.
Okay, thank you. Yeah.
Yes.
Yeah. Good morning, everybody. Thanks for attending our presentation. I am Dr. Bin Chen from Purdue University, Fort Wayne, and our topic is using AI to predict harmful algal blooms in Western Lake Erie area. Okay. Yeah, water quality is of Great Lakes is critical to human health, public safety, fishery, and tourism of the lakes and the surrounding areas. We know that it's a great treasure for this earth. And however, one emerging threat called harmful algal blooms has brought a series of adverse water quality and ecological problems, such as fish death, hypoxia in water body, and more importantly, algal toxins. Western Lake Erie has been facing an ongoing harmful algal blooms crisis since 1960s. So it's between the months of May and August. Normally summer is when water is hot. So HAB are exhibited by the excess of cyanobacteria, which often produce toxins such as microcystins. So direct examination of microcystins is costly and takes time. Sometimes it's maybe a little bit too late to issue warnings. So it would be better to find surrogate water quality parameters for prediction to issue early warnings. So, this satellite image of the Western Lake Erie harmful algal blooms in 2017. You can see this Western Lake Erie area, and also go to Canada. You can see it's the severity is significant. Okay, a couple of more pictures showing the thick algal bloom on the seashore area of the lakes. Okay, so motivations and goal of this research. So the goal of this research is to predict HABs in Western Lake Erie using machine learning. What is machine learning? It's a field of artificial intelligence, AI, that allows systems to learn and improve from data without being explicitly programmed. More specifically, due to limited data of microcystins, chlorophyll A is usually a direct indicator of severity of HABs and is applied as output target in machine learning. So the goals of our research is to answer the three main questions. Which input data are reliable, be used as a training data in machine learning from prediction of chlorophyll A? Which machine learning algorithm is suitable to predict chlorophyll A? And what insights can machine learning provide on HABs? So we have two sources of data. One is remote sensing data, and one is on-site water quality data. So remote sensing data collection and examination. So there are two satellites in the sky we can use for the open data resources. One is Aqui, and the other one is Terra. So we searched and studied several parameters, but finally we focus on the four parameters. One is the sea surface temperature. We know temperature when summer. This is the reason algal blooms happen in summer. Temperature is important. Another one is the normalized fluorescence line light, NFLH, and the diffuse attenuated coefficient at 490 nanometer, KD 490, and remote sensing reflectance at 667 nanometer, RRS 667. All this from satellite data. In the figure one, the intensity of chlorophyll in milligram per cubic meter on July 30th, 2015, for example, based on Moody's Aqui remote sensing data, you can see this map match the Western Lake Erie area. You can compare this figure to the next slide. Yeah, so this is the buoy stations in Western Lake Erie area. You can see the shape here. It's related to the, it's same as with the Western Lake Erie area map. Okay, yeah. So the second source of data is on-site data. It's on-site data. So locations at the Western Lake Erie, including buoy station 2, 4, 8, and 13. And on-site data is from NOAA's Great Lakes Environmental Research Lab online catalog provides two different types of on-site data, weekly data and daily data. Weekly data are collected based on weekly field missions and are recorded approximately once per week, whereas daily data are obtained on-site by buoys equipped with probe sensors and are recorded every 15 minutes. So the hypothesis is the SRP, soluble reactive phosphorus particulate organic carbon, POC, and the total inorganic nitrogen, TIN, and the temperature are these four parameters we want to choose to as the input features for AI learning. Yeah, certainly we started several others, but finally we narrowed down these four. Of course, this is an ongoing research. We can continue include other different parameters and make the prediction better. Yeah, so this figure 2, like I mentioned before, these 4 locations at Western Lake Erie for the data collection. 4 different buoy stations. The green coloration indicates the presence of algal blooms in September 2011. Okay, so first we want to study the reliability of remote sensing data because it's pretty challenging. Remote sensing highly depends on the signals, some kind of water glint, and also cloudy weather condition may affect the signals collection and processing. So the reliability of remote sensing data was tested by comparing daily samples, expecting them to show similar values for the same feature. For example, these 2 satellites, Aqui and Moody's, should be very correlated with each other. So they are both from remote sensing, their signals should be very correlated with each other. So we compare these 4 parameters: sea surface temperature, KD 490, SSRS, RRS 667, and NFLH. We learned, I introduced before, at the 4 different locations. We compare them, use the Pearson correlation coefficient. We want to find high correlation between these 2 satellites. So these indications, the remote sensing data are reliable, we can use. Here is the result. This equation for Pearson correlation coefficient. So X bar, Y bar are the average of X and Y. So we compare these 2 satellites for these 4 parameters: NFLH, KD 490, sea surface temperature, and SSRS 667. The highest correlation between these 2 satellites is NFLH. Next, actually, highest is the sea surface temperature. Next is NFLH. However, the other 2, KD 490 and RRS 667, not so high. So this put us maybe led us to think about maybe this the feature collected from remote sensing are not strongly correlated with each other. So likely it's due to the environmental factors such as disturbance from the glint of water surface and the transparency of the atmosphere like a cloud or other factors. So we decide to put this aside. Later we may pick up again to study the remote sensing data, correlation between remote sensing data and the harmful algal bloom. So we focus on the on-site water quality data at this stage. So we use the machine learning algorithm and evaluations. 12 popular machine learning algorithms were used in this study, including linear regression, polynomial regression, ridge regression, lasso regression, support vector regression with 4 different kernel methods: linear, polynomial, sigmoid, and radial basis function. K nearest neighbors, decision trees, random forest, and artificial neural network. So the evaluation matrix is a mean square error, mean absolute error, and R square. So this shows the equations of these 3 evaluation matrix index we use. Basically we want the first 2 low and R square high. That indicates the high regression and the strong correlation. So this is summarized results from these 12 machine learning models. It's a performance evaluation. You can see the highest R square or the lowest MSE and the MAE happens with random forests. Highest R square we got is 0.84 from the on-site data. So it's not bad. So this the other 11 with a different kind of R square values. The next one is a KNN model is 0.82. So what's the random forest model which has the best regression R square score? Random forest is a machine learning model that uses multiple decision trees to make predictions. It's a popular type of decision tree in ensemble that's often used for classification and regression tasks. So you can see the prediction from the random forests model with all the 4 buoy locations. So Y X is a x-axis is a predicted value and Y is true value. You can see this regression for random forest model with R square 0.84. And Figure 4 shows the lift chart for the prediction of the random forest model. Yeah, for the all locations. Blue curve is a true value, and the yellow curve is predicted value using a random forest algorithm. Okay. So also what are the insights from machine learning we got? Yeah, is the importance of input features. Applying the input perturbation features ranking algorithm helped identify which features was the most important for this study. Also, it's a location dependency. The random forecast model was found performed differently depending on the location of a Western Lake Erie area among the 4 buoy stations. So this table 3 shows the feature importance based on the input perturbation feature ranking algorithm. So MSE and the importance factor, highest one is importance factor, highest one is POC, particulate organic carbon. Yeah. Next is total inorganic nitrogen, soluble reactive phosphorus, and the last one is sea surface temperature. Yeah, it makes sense. Yeah, we know it's a particulate organic carbon closely related to algal biomass, especially during algal bloom season. Okay. This evaluation matrix for random forest model at these 4 buoy stations R squared for this. Yeah, again shows the summary of this random forest algorithm predictions. So this is 4 figures showing the prediction from the random forest model. Yeah, first is for at buoy station 2, 4, 8, and 13 individual buoy station. The random forest algorithm prediction and versus true value shows the relationship. Okay. So this importance ranking for the 4 features based on the input perturbation feature ranking algorithm at these 4 buoy stations. Again, particular organic carbon is highest. Yeah, again, it directly relates to biomass during algal biomass concentration of algae during algal bloom season. Yeah. Next is inorganic nitrogen, soluble reactive phosphorus, and the sea surface temperature. Okay. So conclusions. The studied features from MODIS remote sensing didn't have a high Pearson correlation coefficient between MODIS Aqui and the Terra satellite systems. We are not utilizing this study. Possibly we can continue see the possibility to utilize remote sensing data for better prediction. Machine learning was applied to predict the severity of HABs based on on-site data input features, including soluble reactive phosphorus, particulate organic carbon, total inorganic nitrogen, and the sea surface temperature. Among the on-site data, particulate organic carbon was found to be the most correlated factor to chlorophyll A. After comparing 12 popular machine learning algorithms, random forest model was found having the best performance. This model predicts the value of chlorophyll A with R-squared score of 8.84. The machine learning model was found to be location dependent, and the different structures of the model should be applied to different locations to better predict HABs. Finally, I would like to acknowledge the sponsor of this study, which is our College of Engineering, Technology, and Computer Science. and collaborative research grants from Purdue University Fort Wayne. Yeah. Thank you very much for your attention. I will be glad to take your questions.
Thank you, Dong. So there are some questions.
Okay.
And the one that gets the most upvotes is why use chlorophyll as a target instead of phycocyanin?
Oh yeah, you mean instead of what? Sorry.
Phycocyanin. Phycocyanin is a pigment that's only made by cyanobacteria.
Oh, okay. Yeah, we tried different. We found chlorophyll with existing data. Again, it's ongoing research. We possibly can continue expand the parameters. We can start that parameter as well. Okay. Yeah.
Okay. And then closely related, Claire asks, have you considered adding phycocyanin to your measured parameters, given that not all chlorophyll is from the type of algae that cause harmful algal blooms? It may help improve the transferability of your research to other areas that are not always dominated by cyanobacteria. Also, with respect to transferability of your research, have you considered that other taxa of cyanobacteria besides Microcystis have different temperature preferences? This might explain some of the variation in the model performance.
Yeah, that's a good point. Yeah. So again, we are gonna expand our study by including more parameters and again use machine learning to better predict and make the prediction more kind of adaptive to different environment and wider applications. Yeah.
Great, thank you.
A good point. Yeah.
Grace asks, what are the units on your correlation graphs? Is it milligrams per meter cube chlorophyll A?
Yes, it's a milligram here, the satellite image. Yeah, yeah, this unit, milligram per cubic meter.
Thank you.
Yeah. A lot of data. We need take time to kind of scrutinize which is relevant, which not. Yeah. So this we introduced. We utilize machine learning to help us.
Certainly. How would the importance ranking change in places with agricultural runoff?
Oh, good. That's agricultural runoff would be reflected by nitrogen and phosphorus. Yeah, so this parameter should already include the agricultural runoff and especially the nutrients.
Right.
Normally it's by far it reported Maumee River is the biggest contribution for the runoff.
Harry asks, is it valid to assume chlorophyll A indicates harmful algal bloom? Now, of course, that's a little bit slippery, but I'll let you address it.
Right. Chlorophyll A is one indicator of the could you repeat the question again? Sorry.
Sure. Is it valid to assume that chlorophyll A indicates a harmful algal bloom?
Again, chlorophyll A not necessarily means high microcystins. High microcystin need to use LC-MS to measure it. It takes time. Also, the analysis is costly. Yeah. So again, we want to find the early warning. Yeah. When we detect if the microcystin concentration is high, normally it's already too late. The pollution already happened and gathered already there. So we want to find a surrogate and early indicator. Yeah. They are not necessarily same, but they should be very correlated with each other. Yeah.
This is more commentary than a question, but if you have any counter commentary of your own, I'd be keen to hear it. So Rick Stumpf, who I recognize as somebody quite involved in this field, offers on chlorophyll A versus phycocyanin in Western Lake Erie during the summer, the blooms are essentially cyanobacteria. Phycocyanin is problematic because it is not usually measured in other areas. GLERL, which is the Great Lakes Environmental Research Lab of NOAA in Ann Arbor, GLERL does measure it, and the quantity of phycocyanin per cell varies a lot. So I don't know if you have any thoughts on that, but feel free to offer them if you got some.
Yeah, it's this different kinds of cyanobacteria and different algae. So certainly, it's if we can have a kind of well classified data, and especially targeting the algae can produce microcystin, that would be much better prediction. But by far, we very rare. These data are very limited, and we don't have enough. Yeah. So machine learning is a challenge. The more data available, it can predict better. It can predict better. Yeah. So it's ongoing research. Hopefully, we can have more fine-tuned data and more water quality parameters, especially different types of algae. And so that will be future kind of research directions. Yeah. Mm.
Great, thank you. Now, I noticed the table in which you ranked the
Muted.
importance of the. Oh, I noticed the table in
Can't
which you
hear you.
had. I don't know why I am not muted. So, Anne, can you hear me?
Yes, we hear you fine, Eugene.
I'm not sure why you can't hear me, Don.
I can't hear you.
Could you hear Anne? Anne, can you ask Don if he heard you?
Don, can you hear me?
Yeah.
Don, can you hear
Can't
us?
hear you. Sorry.
That is
Very
odd.
frustrating. Because
That's
I
my
was,
problem. I can't hear you.
you can hear me, Ben.
Yeah.
So I don't know if you can address this, Ben, but
No, I cannot. I don't know much about
okay.
this.
So I was going to comment that the table of ranked important parameters was interesting to me, with carbon at the top, right, and phosphorus at the bottom, because it kind of follows our expectations of a Redfield ratio, but it kind of flies in the face of our expectations regarding what's ordinarily considered a limiting nutrient within freshwater. And now I would very much like to discuss that, but if I'm the only one who hears me asking, I'm not going to be able to discuss that. So um, I'm not sure how to relay this.
Yeah, I'm not sure, Eugene. We're still getting a note. It must be Don's microphone or speakers, excuse me, that are having the issue. Carrie's mentioning that she can hear us. So everyone can hear you except for Don, the one person with the answer.
Yeah, I cannot even pronounce those words.
Well, then, I suppose if somebody could type into the chat and let Dong off the hook, um, we will we will sit casually for 2 minutes before I call up the next presenter.
Okay, sounds
Actually,
good. I will let
probably
him
we can
know.
talk. I can talk a little bit more about machine learning. So
Oh,
this
feel free,
study,
please.
yeah, this study actually is called tabular prediction. It's not a forecast. So currently we got the data and we also did a forecast. So if you're interested, I can send the current results back to you. So we are able to
Sorry, I can't hear
forecast
anything.
in several days for any kind of number or any kind of parameter you're interested in it. For example, the chloride A or other numbers, and we use total different approach to get a time series forecast for panel data. And I'm very happy to know there's a new data set for Lake Superior, and I'm looking forward into it. And I really hope I can process it and let you know what I can find, especially for Kate. So I'm very happy about the new data set.
Great, thank you.
Don, can you hear us now?
No, it looks like he just sent a message that he still can't hear anything. So not sure. I'll ask him to stop sharing though, as we're almost ready to transition to our next speaker. I apologize for that technical issue. Not sure they.
Thank you, Anne. And my thanks to Dong, who can't hear my thanks. So I would like to introduce our next speaker, Connor Keitzer, who is a PhD in fisheries and aquatic sciences from Purdue University, with an MS in biology from Marshall, and a Bachelor of Science in Wildlife Ecology and Conservation from the University of Florida. His research is mostly focused on freshwater ecology and conservation, but he's broadly interested in helping organizations make science-based decisions to improve sustainability, which sounds a whole lot like the mission of Extension. Before joining the Integration and Application Network at the University of Maryland Center of Environmental Sciences, he was the lead data analyst for Western Lake Erie Watershed Conservation Project at the Ohio State University's Aquatic Ecology Lab, and an associate professor of environmental science at Tusculum University. So welcome, Connor, and please take it away. You are our last talk before the short break.
Great. Thanks, Eugene. All right, good morning, everyone. So thanks for the opportunity to talk a little bit about some of the work we've been doing to try and understand how climate change is going to impact the Lake Erie ecosystem, including harmful algal blooms, and the role that conservation practices, agricultural conservation practices, could play in potentially mitigating those impacts. And I'm also going to touch on this talk a little bit about some other aspects of the ecosystem, because one of the really interesting things we're finding is that while we think it should be a win-win, we're actually seeing there might be some trade-offs between kind of nutrient management for Lake Erie and some other aspects of the Lake Erie ecosystem. So I'm presenting this work, but I really need to acknowledge my co-authors who have done the lion's share of the most recent work, including this effort, which was led by Mike Fraker, and he should be the one presenting, but unfortunately he passed away a little over a year ago. So I'm going to do my best to kind of represent Mike in the work he's led, and a lot of this work is the direct result of Mike. So with that said, we are working in the Western Lake Erie watershed. This watershed is dominated by agricultural production. Roughly 2/3 of the area is in corn and soy crop rotation. It's a relatively large watershed, the second largest in the Great Lakes region. It's really valuable watershed. The agriculture production provides roughly $1.2 billion annually to the economy. It's roughly it's roughly 25% of Ohio's overall agricultural production. So a really valuable economic and social watershed. It's also really important environmentally and ecologically. And as many of you are aware, based on previous talk, it has some issues around nutrient loading and nutrient pollution in this watershed. Just to point out real quick, the Maumee River is the primary focus of management efforts in Western Lake Erie. That's that central river you can see kind of running through the middle of the watershed. A lot of the focus is trying to reduce nutrient loading from the Maumee River into the Lake Erie ecosystem. Nutrient issues aren't new for Lake Erie. If we look at a productivity index going through time, we can see that eutrophication really begins in the early 1930s for Lake Erie, kind of rising throughout the next several decades and peaking in the late 1960s. But thanks to things like the Clean Water Act and kind of aggressive management of point sources, we see that nutrient levels are declining through the next several decades, and the ecosystem starts to recover. We see fisheries starting to come back in the lake. over the next several decades. But then in the early 2000s, we see this issue of eutrophication coming back as a result of nutrient pollution. And in this case, we know that the major culprit is non-point source pollution, largely from agricultural runoff, with a big focus on phosphorus and the role that phosphorus is playing in harmful algal blooms. As a result of this, we see harmful algal blooms in Western Lake Erie pretty much every year now. So looking at this bloom severity index from NOAA through time, you can see that it is a consistent problem. It's a common problem. And it's, especially in the last 10 to 15 years, we're seeing pretty severe blooms occur in Western Lake Erie. So this has led to a lot of concern and effort over the last 15 to 20 years to try and address this issue, primarily by reducing phosphorus loading from the Maumee River into Lake Erie. The primary approach for doing that is to increase the amount of agricultural conservation practices that are out there in the watershed, with the idea that this can help reduce nutrient runoff and improve water quality in Lake Erie. This is a little old, but it just gives you an idea of the practices that are currently in the watershed, lots of different types spread throughout. A more recent map would look even more crowded. And what we're finding is that it can help, and these practices are going to help, but it's still going to be challenging, even if we implement practices pretty widely. So this is a figure from a study led by Jay Martin from Ohio State University, where they looked at five different watershed models that kind of simulate nutrient loading into Lake Erie across realistic conservation scenarios where, they got stakeholder input from a variety of people, including farmers, about what types of practices they would like to see put in at what amounts and what kind of adoption rates. And what this study found is that for both total phosphorus and dissolved phosphorus, it's going to be a challenge to meet sort of these nutrient loading goals, the target for Western Lake Erie, based on realistic conservation scenarios. So across the board, we can look at, if you consider a goal of meeting that 9 out of 10 years, we see that in most cases, we're going to fall short of that. And it really is going to be challenging to meet those goals. And this is before you start thinking about the role that climate change is going to have. We know climate change is already impacting the system and changing dynamics. These figures show, on the left, I'm showing number of high kind of runoff events or high rain events that are occurring through time in Western Lake Erie watershed. We have two lines. The dark line, or the solid line, is representing, fairly extreme runoff events, or runoff events, and then the open circles represent really extreme, and then kind of upper 90th percentile of observed runoff events. And that's increasing through time. And this we would expect to result in increases in phosphorus loading to the lake, both total phosphorus and soluble phosphorus going into Lake Erie. There's a pretty strong correlation between runoff, spring runoff, and loading into the lake. And we think it's going to get worse. So these figures are showing precipitation change and temperature change on the x-axis for two different climate scenarios. So the blue kind of square represents moderate reductions in greenhouse gases, and the red is the business as usual type approach, so fairly high levels of greenhouse gases. The panel on the left shows kind of the near term, so now the 2020s, what we are expecting to happen. We're going to see some increases in both precipitation and temperature. And that's expected to increase even more as we move into the future. So if we look at kind of the mid-century, the 2040s, it becomes even worse potentially, or more extreme, I should say, for the area, especially if we aren't able to reduce greenhouse gases in the watershed or in the atmosphere. So this has the potential to really alter the effectiveness of these conservation practices, changing runoff, changing growing season. It's kind of a complicated potential interaction of effects of climate change. So what our group has been trying to do is understand and forecast, or at least explore, I'm not going to say predict, but explore what this might mean for Lake Erie, when we start thinking about climate change and these conservation practices. I also want to mention we've been working not just on harmful algal blooms, but other valuable or important parts of the ecosystem. And today I want to mention or talk a little bit about the potential impacts on Lake Erie fisheries and stream biodiversity. So when we think about Lake Erie fisheries, it's also really valuable, especially walleye and yellow perch. It's roughly 1.5 billion annually in commercial and recreational value. And looking at the figure on the left, we can look at the relationship between commercial harvest and a productivity index. For 3 different species, or commercially important species in Lake Erie, we have yellow perch. They seem like they're going to do a little bit better potentially with nutrients. Walleye have sort of this non-linear relationship where they need, they need a little bit of productivity or a little bit of nutrient kind of input to boost production, but then it could get bad for them if things get too extreme. And then whitefish really like kind of more low nutrient conditions, more mesotrophic or oligotrophic type conditions. So that when we think about the effects of climate change and managing for nutrients, we may see sort of trade-offs among these species, just looking at kind of current trends and relationships. The same is true for stream biodiversity. That watershed is home to 98 different species of fish. Over 40% of them have experienced large population declines, and several have gone locally extinct. And we know that they're strongly influenced by water quality, things like nutrients or sediments, which is what I'm showing in this graph, where if we look at our predatory type species, they're negatively impacted by increasing sediments. So we would expect in implementing these conservation practices to benefit a lot of these stream fish, but we don't know. So we kind of want to ask that question and explore that as we look at managing nutrients. So kind of our objectives for the rest of this talk is understanding how agriculture conservation practices could help reduce the harmful impacts of climate change on harmful algal blooms, and then also briefly discuss some potential trade-offs with things like stream biodiversity and Lake Erie fisheries. I don't want to get into a lot of detail on the models, so I'm just going to provide a general overview. Our approach was to link physical and biological models to explore these impacts. So we have climate change projections, which provide us information on rain and precipitation, and also temperature. The outputs from those scenarios are inputted into our watershed model, which we use the SWAT model, which is commonly used to look at nutrient dynamics, flow, hydrodynamics, and kind of overall like loading into Lake Erie. So we simulated water quality and those sort of things across the watershed and linked that to models of fish. So we have fish recruitment or presence absence of stream fish related to some sort of habitat attribute. And then our cyanobacteria model for HABs. I won't go into much detail on the models, but I do want to mention the cyanobacteria model for today's audience. So we used a really, relatively simple model based on the work by Rick Stump, looking at an index of severity for harmful algal blooms based on just spring flow into the watershed, and then flow-weighted total phosphorus concentration for us, because that's what our model was calibrated for. We don't have soluble reactive phosphorus, so we use total phosphorus. You can see, generally speaking, it does a decent job of predicting blooms, although we may be missing some of the extreme events, either high or really low at high loading or low loading levels. So our goal here was to provide simple but hopefully informative kind of information about what the future could look like. But we fully acknowledge that it's a limited model, and there are more sophisticated ways to look at this. For our climate projections, we chose two. So this figure is just showing the carbon dioxide in the atmosphere per year through time. We use the extreme sort of business as usual, so we kind of continue on our current path, what that might look like. And then a moderate reduction, this blue line, kind of as a realistic goal for reducing carbon dioxide emissions. And then we had four conservation scenarios or agricultural conservation scenarios. We have the baseline, which is basically if you imagine just freezing the current amount of conservation practices in the watershed and looking what happens through time. We have a scenario where we treated just the critical acres as identified by the NRCS, which represent about 8% of the acres in the area. The critical and moderate acres, which represent about 48% of the area. And then if we were to, add practices all over the place, 96% of the area, what does that look like? We used pretty standard conservation practices. One of the ones that is missing from our modeling approach is wetlands, because we didn't have that information at the time. But we do cover most common sort of nutrient management and erosion control type practices in the watershed. So let's jump into the results. So the graphs are a little busy because we do have 8 scenarios that we're looking at. So when we look at the impact on HABs, if we look at the percentage of years per decade where we have really severe blooms, so that's an index greater than 7 on our for our HABs, we can look at the percentage of years kind of where that occurs. So 0 is good. 100% would be bad. So that kind of dark green means we're seeing HABs every year, basically, during that decade. We have 2 panels I'm going to show. So we have our climate change getting worse on the bottom panel. The top panels are more moderate type of climate change. And then conservation practices, those scenarios increase as you go from the bottom to the top of these figures. So we're increasing the amount of conservation moving from the bottom to the top. So if we look at our moderate kind of climate scenarios, looking into the mid-century here, a couple of things I want to point out. First off, if you're kind of just curious about the impact of climate change, based on our model, if you look at this base row and kind of through time, you can see that climate change is expected to increase harmful algal blooms. For us, that was due mostly to increased loading in total phosphorus as a result of those high runoff events into the watershed. But if we were able to put conservation practices into the watershed and adopt those widely, we can reduce the impacts of climate change, especially if we were to do that across the whole watershed. We could help at least limit the amount of severe severe effects of climate change on harmful algal blooms. But it gets more challenging as climate change gets worse. So again, this dark green is bad. And depending on how extreme weather gets in the future, we'll need more practices in place to make that happen. This is showing the goal that one of the goals is to get to have a kind of annual index of harmful algal blooms below 2.9. So this is kind of the same information, but just looking at a slightly different way. In this case, dark blue is good and the light blue is bad. And we kind of see similar things where if we increase conservation practices, we can help meet these goals. But as climate change increases, it gets harder to do that. And our modeling suggests that it's not going to be an easy fix where we can just treat just critical acres to meet these goals. We're going to have to do a lot all over the place to try and reach these goals. All right, so next I want to talk a little bit about the impacts on stream fish. So we have a slightly different setup here where conservation practices increase as we go from left to right on our bars. So we have light gray, the dark, meaning conservation practices are increasing. Time is we're gonna show 2 panels for time. So near term, kind of the next couple of decades at the top, and then long-term, midterm on the bottom. Climate change gets worse as you go to top to bottom on each of these panels. And the results I'm showing are the net change across 19 different species that we developed models for fish in the watershed that we felt confident in their ability to predict suitable habitat. So we're going to look across all those. What is the net change in suitable habitat in the watershed? And what we find is that in the near term, under moderate climate, so this top part of the panel, increasing conservation practices should benefit stream fish overall. But in the more extreme case of climate change, it kind of overwhelms the ability of these practices to benefit stream fish. We also can think of things like temperature starting to play a bigger role here. But still, implementing these practices over a big area could help mitigate some of the effects of climate change, kind of indicated by this graph. So we see a net loss overall, but the conservation practices could help offset some of that at least. In the long term, though, what we find is that climate change is really kind of overwhelm the ability of conservation practices. You can see that there's no real change across the amount of conservation practices we put in. And in the long term, we're going to lose habitat potentially for our stream fish. It's not, when you start digging in, it's more complicated. I won't spend a lot of time on this other than show that these are the individual species that we modeled. And what we find is that there are trade-offs. So some species, like brook silverside, greater red horse, green darters, for example, are going to do a little bit better in the future, especially if we can put in conservation practices. Whereas others, like log perch and mottled sculpin, for example, are going to do worse. And actually, putting these practices could exacerbate that a little bit and make things a little bit worse for those species. So there's winners and losers potentially for our stream fish. And we see something similar for our lake fish. So again, just set this up because it's another way of a slightly different way of showing things. So we modeled yellow perch, a really important recreational and commercial species, white perch, which is an invasive species, and then walleye, another really important commercial and recreational species. And we looked at the frequency of strong recruitment events that are going to occur through time. We have climate change getting worse from left to right on this panel, and then conservation practices increase from top to bottom. And I'm only going to show two scenarios. So basically putting practices everywhere, because what we found is that conservation practices, and for yellow perch anyways, are going to have a limited impact. And most of what is happening is driven by climate change. This solid line shows you historically what the average frequency of strong recruitment events. The purple line I just put in here as reference because that's what's happening. And basically, climate change is going to be bad for yellow perch, or worse for yellow perch. And the practices, it's kind of a mix, but they might actually make things a little bit worse. Yellow perch is that species that does a little bit better and more productive ecosystem. And then as climate change increases, things get a little bit worse for yellow perch, basically. And it's kind of overwhelming the ability of these conservation practices. White perch, we found a slightly different story. White perch, if you look at the baseline, there's no real big impact of climate change. It's just kind of variable. But if you look at conservation practices, putting in those conservation practices might actually benefit white perch, which is great for white perch, but maybe bad for the ecosystem because they are an invasive species that can impact food webs in Lake Erie. And then for walleye, last one, walleye, we found really no effect of the nutrient loading or conservation practices on walleye. It was all driven by climate change and the effect of climate change, and more or less things are going to get worse for walleye in the future, potentially, as climate change alters things like winter warming rate and the overall severity of winters for walleye. So to kind of summarize this information, What we're starting to find, or our modeling suggests, is that there might be trade-offs in managing for nutrients and fisheries production and biodiversity as well. For HABs, what we find is that climate is going to increase HABs potentially, and conservation practices could offset that. So conservation practices should reduce HABs. Overall, if we put these things in and adopt them widely, it should be a win for the ecosystem. For our Lake Erie fisheries, it's a little bit different. Walleye are going to do worse in changing climate. Conservation practices, no real effect. Yellow perch are going to do worse with changing climate. And conservation practices might actually make that a little bit worse. The white perch, no real effect of climate change, but they do better with these conservation practices. So that's sort of a loss for that part of the ecosystem potentially. And then streamfish is complicated, and there's lots of different species, and there's wins and losses across these species. And I think sort of the take home from our work and what we're finding is there's a real need for ecosystem-based management because as we manage for different parts of this ecosystem, we may unintentionally negatively impact other parts, and we really need to be considering these things as a whole so that we can arrive at sort of management decisions that we're all are mostly okay with and happy with. So a lot of people to thank. These are some of the groups and agencies that have supported this work or collaborated on this work. If you're interested in learning more, please just send me an email. Here, my contact information here. If you want to read more about this paper, it is open access. You can scan the QR code to access that paper. I can also send you other papers related to this if you're interested in it. And thank you all for your attention.
Thank you, Connor. I can't say that's a very hopeful message, but it certainly is potentially a useful one. There are a couple questions,
Okay.
and I'm not sure that you're the one to answer the first one, but I'm going to ask it just the same. Who has a handle on the number of Hickenbottom tubes used in the Western Lake Erie Basin um, watershed, mostly within Ohio?
Yeah, I'm not the one to answer that. Sorry. Hopefully, maybe someone else on the meeting can. I have no idea.
Yeah, I also have no idea, right? That's a drainage structure thing, but I just don't know who's got the handle on that.
Yeah.
Um, James asks if both yellow perch and walleye populations are expected to decline over the next 40 plus years. Are there any thoughts of what species might fill the niche they would be opening?
Yeah. White perch, it's looking like, unfortunately. Um, but I don't know. I'd have to talk to Stu Lutson at Ohio State. He would have a much better answer to that, I think. But definitely white perch look like they're going to be fine, unfortunately.
Now, this is a side note, but I grew up fishing Lake Erie, right? And
Mhm.
I fishing for white bass, which of course are congeners of white perch, and there were some tricks that I used to differentiate those two species in the field that were really quite handy. However, it seems to me in recent years, some of those differences, especially so there is a gradation of anal spines. And in the white bass, you've got a short anal spine, a medium anal spine, and then a long one. In the white perch, you've got a short and two long. It seems to me that that distinction is being lost. Do you have any sense from your collections if there's hybridization going and if climate might even contribute to that?
I don't, but that is an interesting question. I just don't know the answer to it.
Thanks
So,
for trying. Sorry for putting you on the spot. One
okay.
last one, hopefully that from Laura, hopefully that you will have a handle on. Can you talk a bit about your exploration of targeted versus widespread ag conservation practices and their impact on reducing nutrient loss? The presentation looked like widespread practice adoption, whether random or not, would have more impact than targeted practice implementation.
Yeah, so our targeting was focused on treating what the NRCS considers critical acres based on, slope and current practices and those sort of things. And what we find is that if you're considering like the cost benefit, that's the best way to go because you get the most bang for your dollar by treating those critical. But when we think about the amount of acres in need in that watershed, um, we find you need more widespread adoption, especially if you're thinking about improving conditions across the whole watershed, for all the streams and rivers. Treating those critical areas could be really beneficial for Lake Erie, but might not capture or achieve a whole lot for the whole watershed.
Great. Thank you, Connor. And that puts us at a very good time to break, seeing no more questions. We will now break. We will reconvene at 10:45 Central. That's 11:45 Eastern. And I just checked. There's no line at the bathroom. So I'll see you in 15 minutes. Goodbye, all. And to do so, I'd like to introduce Dr. Sony Kumari, a postdoctoral research associate in the Department of Biosystems and Agricultural Engineering at Michigan State University, with a PhD in Environmental Science and Engineering from IET Dhanbad, India. Dr. Kumari specializes in developing cost-effective and sustainable strategies for wastewater treatment and nutrient recovery, aligning with the core philosophy of creating wealth out of waste. Her current research focuses on capturing dissolved phosphorus from controlled tile drainage in the Western Lake Erie Basin. Dr. Kumari has authored 12 peer-reviewed publications and 3 book chapters, contributing significantly to the advancement of strategies to mitigate nutrient pollution and promote sustainable water management. I'm very glad that she could join us. Welcome, Dr. Kumari. I'm eager to hear your presentation.
Yeah, can you see my screen?
It looks good. Yes, thank you.
Yeah, okay. Hi, everyone. Good morning. And it's good to be here at this annual Algal Symposium. A lot of, like, all the 3 presentations were quite insightful, and all were revolved around monitoring of these algal blooms around the lakes of the United States. So here I'm to present my insights on my current research work, which deals with the evaluation of alkaline media for phosphate adsorption from subsurface drainage water. This is directly linked to the problem which could address eutrophication and this algal bloom proliferation in the aquatic water bodies. We all know that phosphorus is an essential nutrient for agriculture productivity, but its continuous draining into the aquatic bodies has made it is a major pollutant which is being discharged from agriculture drainage system. Subsurface drainage water is a byproduct of agriculture land management practices, often carries significant amount of dissolved phosphorus in the form of phosphate. This persistent discharge of dissolved phosphorus into the aquatic bodies causes this harmful algal blooms and compromise the water quality. So there is need to reduce the loads of this phosphorus from the agriculture drainage catchment areas at the source itself, so that it will not impact our water qualities, which is in the downstream of these catchment areas. According to the Environmental Protection Agency regulatory standards, there are certain limits for release of these phosphorus into the lakes, that is 0.05 milligram per liter, and into the streams, it is 0.1 milligram per liter. For agricultural water, it's 0.1 milligram per liter. So here we need to devise certain methods so that it can be recovered in some useful products which can be reused for the further. There have been treatment methods for removing these dissolved phosphorus from the tile drainage water, and these traditional treatment methods are buffer strip, wetlands, and cover crops. But these things have their limitation. They have the land availability issues. They are dependent on the critical weather conditions, as well as maintenance of these things are quite a tricky thing and labor intensive work. So these does not work that well, but it has done some, these methods have done certain successes in removing the dissolved phosphorus from the agriculture water management catchment areas. Nowadays, researchers are more focused on phosphate removal structures, which utilizes different phosphate sorbing materials, such as natural materials, which are, for example, like dolomite, limestone, zeolite. But these natural materials, when synthesized or modified with certain metal oxide, hydroxides, it gives more significant phosphate recovery or removal from the water, any source of water which has this higher concentration of phosphate, or even the lower concentration of phosphate, which might cause problem when it's piled on continuously into the aquatic bodies. Besides, there have been many works done. There is always a continuous need for developing an innovative, cost-effective technology which can capture phosphorus, and it has a reuse potential. For the current study, we are using an alkane media, which is an iron-activated aluminum media, which is commonly marketed for arsenic removal from the water. So we are testing this alkane for removal of dissolved reactive phosphorus from the subsurface drainage water. The objective of our works are to optimize the key parameters. We have started the experiment with the basics, where we would be learning the isotherm and kinetic behavior of the alkane media for removal of phosphate from the subsurface drainage water. And then we will be going on to the next stage of the work, that is the column study and the field installation, which is already going on. So for this particular presentation, we are focusing on basic isotherm and kinetic studies and the regeneration capacity of the media. So the current objective are to optimize the process parameters such as contact time, adsorbent days, that is the dose of the alkane media, pH at which it gives the maximum phosphate removal, and initial phosphate concentration for maximum phosphorus removal efficiency. Second objective is to investigate the adsorption mechanism of alkane through isotherm and kinetic studies. And third was to regenerate the phosphorus saturated media on a batch scale study mode. So the methodology for the current work utilizes small batch scale reactors, which was done. It's a basically adsorption study which was done in incubator shaker in a small conical flask, where we have tested 4 parameters in different ranges. The contact time for alkane and phosphate solution was varied from 1 to 10 hours. Adsorbent dose was selected from 1 to 7 gram per liter. pH was varied from pH 3 to 11, and initial concentration was varied from 1 to 10 milligram per liter. On the basis of these parameters, phosphate adsorption capacity and percentage phosphate removal were recorded, and data were analyzed for maximum phosphate removal capacity and isotherm study. For the isotherm study, we have used 2 models, Langmuir and Frenlich. And for kinetics, we have used the 2 models, pseudo first order reaction and pseudo second order. These models help us in establishing, theoretically calculating the equilibrium concentration of the phosphate and the time at which the maximum phosphate removal can be achieved. So these basic information are important for designing a large-scale adsorption system, or the filter being designed using these phosphate sorbing materials. So this is the pictorial representation of the methodology where we have characterized the alkane media, which was then subjected to the batch scale adsorption study, and the results were drawn from this scan. This work has been published recently, so you can also check on that. Results. This graph talks about the effect of alkane dose as well as contact time on percentage phosphate removal. From this figure, we can easily see that when the contact time was increased from 1 hour to 10 hour, there was increase in the percentage phosphate removal, but up to 6 hours of the contact time, there was significant increase in each condition, but it kind of showed very slight difference in the percentage phosphate removal when the contact time was increased over 6 hours of the time. This might be due to unavailability of the vacant adsorption site after the equilibrium was achieved at this 6 hour of the contact time. Also, the dose of the alkane was increased from 1 to 7 gram per liter, but we can see that from 1 gram to 3 gram per liter, there was significant increase of 64% to 95% till 6 hours of the contact time. But when the dose was increased from 3 gram per liter, there was not much difference, maybe because the adsorption surface area was saturated and active sites were not available for further adsorption of phosphate. So from this graph, we infer that contact time of 6 hours and a dose of 3 gram per liter of alkane was optimum for 95% of the phosphate removal. From these two graphs talks about effect of pH and initial concentration on phosphate removal. This graph shows the effect of pH where we have varied the pH from pH 3 to pH 11. We can clearly see that there was increase in the percentage phosphate removal when the pH was increased from 3 to 7, but it gradually decreased when the pH was alkaline and it declined drastically at pH 11. So it can be said that in alkaline pH, there is release of different phosphate ions, which causes increased phosphate removal. But in alkaline condition, there is release of hydroxide ions, which competes with the phosphate ion so that the percentage phosphate removal is declined. Also, we see that there was maximum phosphate removal at pH 7, which was neutral, and the pH of our subsurface drainage water was around 6.8 to 6.9. So, for the further experiment, we have not changed the pH of the solution because we got maximum phosphate removal at neutral pH. This graph shows about the effect of initial phosphate concentration on phosphate removal. Here we can see that as we have increased the initial phosphate concentration from 0.5 milligram per liter to 10 milligram per liter, the percentage phosphate removal dropped. This there was increase in the percentage phosphate removal at like lower initial concentration because there were availability of active sites on these lower concentration of phosphate on the alkane media. But as the concentration increases, the active sites on the alkane media was saturated and it has resulted into a decrease in the percentage phosphate removal. These two graphs talks about the adsorption isotherm for the adsorption of phosphate on alkane media. As we have tested two isotherm, linear Langmuir isotherm and linear Freundlich isotherm. Langmuir isotherm says about monolayer adsorption of phosphate on alkane media, and Freundlich isotherm deals with the multi-layer adsorption of any ions on an adjacent surface. In our case, based on our experimental condition, we found that Freundlich isotherm best fitted our experimental condition based on the R-square value of 0.99, which was close to unity. So, and also this adsorption intensity was 2.6. So we inferred that in our experimental condition, there was multi-layer adsorption of phosphate ion on the alkane surface. The adsorption kinetics was evaluated based on two models, pseudo first order kinetics and pseudo second order kinetics. First order kinetics talks about physical adsorption of any adsorbent physical adsorption of phosphate on alkane media, while pseudo second order kinetics deals with the chemical adsorption of phosphate on alkane media. From this graph, we can clearly see that the R-square value was close to unity in case of pseudo second order kinetics, suggesting that there was chemical adsorption of phosphate on the surface of alkane media. Also, the calculated QE value was 0.65, which was close to the experimental QE value of 0.63, which further suggested that pseudo second order kinetics fitted well with our experimental condition, and this is a chemical adsorption of phosphate ion on alkane media. These are the structural morphologies of alkane. This is before adsorption and this is after adsorption. Before adsorption, we can see the roughness and the cavities on the surface of alkane media, which disappeared after adsorption, which further suggests that there was adsorption of phosphate because there was occurrence of phosphate peak in the EDX mapping done for elemental mapping of the alkane we did before and after. So these characterization and structure morphology and elemental analysis shows that there was adsorption of phosphate on the alkane media on the alkane surface. On the basis of experimental results, adsorption, isotherm, and kinetics, we have developed a probable mechanism for phosphate adsorption on alkane media. So there were two types of mechanism going on the surface of alkane. One was electrostatic attraction and another was ligand exchange. Because alkane has the aluminum iron, which is a positively charged ions, and phosphate being a negatively charged ion, there was electrostatic attraction among them, which causes removal of phosphate in the subsurface drainage water. Also, there is hydroxyl groups and the water molecules on the surface of alkane, which led to the pairing of phosphate ion to the hydroxyl groups on the alkane surface, leading to ligand exchange. So we can say that phosphate was removed through alkane media based on these adsorption mechanism, and there was multi-layer chemisorption of phosphate on alkane media. This graph talks about the reusability of the saturated media, alkane media. And for the regeneration study, we have used 0.1 molar potassium hydroxide solution, and the adsorption and desorption efficiency were checked till 6 cycles, and the results were very consistent throughout the 6 cycles, where we see that there was more than 93% of the adsorption efficiency in each cycle, and the desorption efficiency for the first cycle was around 89% and decreased to 75%, and it became constant after that. So in each cycle, there was a good efficiency of phosphate adsorption, which clearly suggests that this alkane media can be regenerated and can be used in multiple cycles. Though it is a batch scale study, we still need to check in the column study so that it can be used effectively in the field scale studies. So this gives an idea that this media is it can be regenerated, and it can be a cost-effective method for removal of phosphate from subsurface drainage water in the field when we apply these media in the phosphate removal structures. The conclusion of the current work is that based on the isotherm studies, the optimal conditions were 6 hours of the contact time, 3 gram per liter of the alkane dose, and the pH was 6.8. Franlich isotherm and pseudo second order kinetic model best describe the adsorption process, suggesting that there was chemical adsorption of phosphate on the alkane surface. The maximum phosphate adsorption capacity was 2.6 milligram per gram for alkane media. And also the potassium hydroxide was able to regenerate the alkane media, and the adsorption efficiency was more than 93% for over 6 cycles. So these are the future studies we are currently looking into. So optimization of process conditions and evaluate the alkane's performance in dynamic system using fixed bed column experiments. Evaluate the effectiveness of phosphate capture boxes, which is already installed in the fields for removal of these dissolved reactive phosphorus from the agriculture drainage water. And lastly, the techno-economical analysis of using alkane media and phosphate removal structures. So this is, I would like to thank people involved in this work. So I would like to thank funding agency, that is the Michigan Department of Environment, Great Lakes and Energy, Thad Cleary from Eagle, and the lab members who has helped me during the course of the experiments in the lab. So I would like to thank everyone who is involved in this work. This is it for the presentation. Thank you, and I'm open to the questions.
Thank you, Sony. We have a number of good questions. So first, there are a couple that I'll ask by Ed. Ed says particle size appears small. How does a phosphorus structure overcome the high pressure drop, especially when media begins to foul or scale?
Okay, so could you please clarify these questions a bit more?
So I'm wondering how. Well, this is Ed's question, so there's only so much clarifying I can do.
Yeah.
But there is going to be a pressure drop, right, when the media begins to foul, and I'm wondering how the system overcomes that.
Because this whole setup of the treatment boxes are in the process of installing, and we are looking into different aspects of that. So we have a team who are dealing with these engineering stuffs. So I think I need to check with them to answer these questions.
Thank you. Ed also asked, how does contact time in hours respond to heavy rain events and significant flow rates? Doesn't one need a media with contact time in minutes for farm runoff or drainage waters?
Yeah, for our because this the study which I have presented here is a batch scale isotherm study, so the conditions are totally different here. But in the fields, we are going with 1 ml per minute of the flow rate. So the empty bed contact time for our phosphate structure in the fields which we are going to deal with is the 1 minute of the empty bed contact time. So that is a small contact time, and we'll be dealing with that high flow rates.
Great, thank you. Paul asks, were any tests done below 1 milligram per liter initial phosphate? You mentioned limit in lakes is 0.05 milligrams per liter. Is there an ultimate equilibrium limit to phosphate removal?
Actually, we have taken an average, and we have, for all experiments, we had kept the initial phosphate concentration to 2 milligram per liter. And also, while checking the initial phosphate concentration, the lower limit I selected was 0.5 milligram per liter to 10 milligram per liter for the adsorption isotherm and the kinetic studies. So, going down than that, I need to check up on that.
Thank you. Ed again asks, where in subsurface drainage waters contain 10 milligrams per liter phosphorus? That's a lot of phosphorus.
Yeah, that's what. Because this is a lab scale study. When we are going into the for getting into the isotherm and kinetics, we need to check on the different initial concentration. We can't have the isotherm and the mechanism established based on the one concentration of phosphate. That's why we have selected the lower ranges, that is 0.5 milligram per liter to 10 milligram per liter. So that's for the isotherm and the adsorption kinetics.
Great, thank you. Now, Stewart offers interesting results and goes on to ask, using SRP dosing levels of 1 milligram through 10 milligrams per liter seems a bit high. Are there plans to repeat experiment and reduce the dosing concentrations to levels suggested between 0.05 to 0.5 to understand better how Alcan can assist with achieving removal of soluble reactive phosphorus in order to reach the limits, US EPA generalized limits presented for lakes, 0.05, that is, and streams, 0.1, which I assume to be for total phosphorus and not soluble reactive phosphorus.
Okay, thanks for the suggestion. I'm also looking into decreasing the concentration to 0.5 milligram per liter as has been recommended by the US EPA. So yeah, I'll definitely be looking into that area.
Thank you. Any field trials in progress or planned? Asks John.
Yeah, actually, we were planning to start by October this 2024, but unfortunately, due to some installation issues and those things, we were not able to run the experiment. So we are hopeful that the removal structure will operate in the month of spring.
Great, thank you. Ed again asks, would higher concentrations of KOH achieve greater desorption recovery percentage?
For the lab experiment, I have tried with 0.1 molar KOH and 1 molar KOH, but 1 molar KOH with small setup reaction was not giving consistent results. So I have selected 0.1 molar of KOH. When I will be dealing with the column study, I will definitely going to check the higher concentration of KOH. So there have been study which deals with higher concentration of these alkaline eluting agents. But while I checked for these small setups, the results were not consistent with 1 molar of the KOH. So I selected 0.1, which has shown a good results, a significant results, and a consistent results.
Great, thank you. Carrie asks, do you anticipate that any other ions in field conditions might bind to the media, decreasing the capacity for phosphate absorption?
As the characteristics of the drainage water suggest, and what we have checked till now, we haven't came across any interfering anions affecting the phosphate removal using this alkane media. So I don't think so. There is some concern about that because we have checked those things.
Thank you. Laura asks, there is a lot of really active discussion, so thank you for your time in answering these questions. So Laura asks, does your team have plans to expand this trial to field experiments, which is something you've already kind of answered. So
yeah.
I'll take it. If you want to add anything, feel free. Otherwise, we'll move to the next question.
We are already have installed 3 treatment boxes at 3 different fields where we will be checking the around year data and collecting 3 years of data. So we will have the idea that how efficient these treatment boxes are for removing these reactive phosphorus from the agriculture trial drainage system. So we are extending this work.
Great, thank you. Aaron asks, when the Alcon is generated with the KOH, does that release phosphorus itself? That is, will the P get released to surface water later?
Okay, so why we do use this KOH, we won't be doing it that it should be going into the surface water. We will be doing the regeneration in a controlled condition so that the media which is saturated into the removal structure will take out those media. It's in the bags, and we will design a different kind of reacting system where we'll be applying the KOH so it can regenerate the media, and then we can reuse that media again into the phosphate removal structure. So we will and also we can also, one thing we have thought of, that this KOH solution which has the phosphate in it, can be used as a fertigation agent, that a solution which can be used for irrigation as well as fertilizer, because it has both phosphorus and the potassium. So it can be used as a fertigation agent when diluted to certain condition, which is good to be used for the crops being. So these study needs to be tested. So we are looking into holistic approach of utilizing these media and all those things.
Great, thank you. Ed asked for your email address, but I want to point out that it will be on the slide that concludes this session. So watch for that, Ed. And if you don't catch it, then write to the organizers, please. And the last question that we've got to get to very quickly, would heavy metals interfere in the absorption, especially when you work with runoff?
Because we haven't looked into any heavy metals like that, so I need to check upon these heavy metals interference. As far as alkane is concerned, I don't think that it would be a matter of concern, but yeah, we need to check on this.
And one final question appeared in the question and answer panel, but we don't have time to get to it. If you could take a little time to type that answer, Sony, it would be appreciated. Thanks for an excellent presentation.
Thank you. Thank you so much.
So moving on to our last talk of the morning session, I'd like to introduce David Shackleton, who heads SysBio, the leading biotechnology company in the water sector. SysBio has developed solutions to eutrophication, hypoxia, and harmful algal blooms from first principles that have been successfully implemented in Asia, Africa, and the U.S. Their one biotechnology solution platform targets the root causes of eutrophication, as recommended in the 2022 Government Accountability Office reporting on managing the risks of hypoxia and harmful algal blooms, and delivers consistently to reverse eutrophication, eliminate hypoxia, and prevent toxic cyanobacterial HABs. I'm interested in the subject of this talk in particular because I do a lot of work with pond management, and I'm eager to hear what David has to say about algicides in this context. So carry on, David. Welcome.
Thank you. Yeah, I guess this whole issue of eutrophication is a global problem, and the word itself, I think, is very misunderstood, particularly in this part of the world. People seem to think that eutrophication means too much of an elevated nutrient level. The root of the word comes from the Greek and actually means well-nourished. So what that means really is what you have to look at is if these nutrients are entering the water and you have a well-nourished situation, why is that a problem? What is it that's well-nourished and what is it that isn't well-nourished? Which means you're really getting drawn into the basic nutrient cycle where nutrients produce biomass dies off or excretes, and that decomposes to produce nutrients again. So what you have is a fundamental disruption in the nutrient cycle. And so our approach is, get back to basics, first principles, as we said. So in any water body, you're always going to have nutrients flowing in. In an optimal situation, that's naturally your primary biomass produced is algae. The food web, and we've got two little fish there, but we're talking everything really from zooplankton upwards, they will consume that algae. It's processed through the food web. That food web includes land-based animals, and so you have a nutrient clearance mechanism in place. As long as that balance is maintained, you don't have a problem. What happens then is you get an increase in nutrient inflows, and a lot of that is obviously anthropogenic, and more algae than the food web can consume is produced. So it's a bit like having a big banquet at a wedding. Everybody eats what they can. There's a whole lot left over. What happens with the leftovers that can't be consumed before the algae dies off is it sinks to the bottom, decomposes. And this is where the problem starts, because you start accumulating organic sediment, which is nutrient rich, in shallow areas. Obviously, the first symptoms you're going to see will be invasive weeds that can grow in that environment, whereas your indigenous weeds that are looking for a sandy or harder bottom are not going to be able to thrive. And then because you have an ecosystem, you have to start looking at systems-based processes and things like feedbacks and tipping points. So as the organic sediment decomposes, you'll have oxygen depletion from the bottom, so you start getting hypoxia. Then obviously you'll get nutrient uploading, recycling from the sediment. And so you have a secondary nutrient cycle that's set up. And we have more and more algae being produced. And because there's more algae present, when you have inflows, there's more algae available to capture those nutrient inflows and convert it into more biomass. So you have feedback loops going on. The life of algae cells is typically measured in days. So in short cycles like that, you're constantly compounding the nutrient deposits in the sediment. Eventually, the hypoxia will get to a point where the animal life in the food web cannot exist or maintain their operations throughout the water column. There are large areas of the sediment that become anoxic, and so your benthic zooplankton are obliterated. They cannot function there. So again, you've got feedback mechanisms going on. So one important metric that we should be looking at is what proportion of the sediment in a lake is hypoxic or anoxic, because in those conditions, the microbiology changes, the benthic zooplankton doesn't function, and the whole recycling of nutrients takes on a different line. Your nutrient clearance mechanisms are constrained because the food web is constrained. So now you have continuing feedback until you get to tipping point. So the real things we've got to be looking at is the nutrient stockpile in the sediment, the degree to which hypoxia is taken over, and understanding the nutrient recycling. Because what happens over time is it gets to the point where the nutrients recycling from the sediment is sufficient to become self-sustaining. And the more these feedback cycles go on, you get to a point that your nutrient clearance is suppressed to such an extent that even if we reduce nutrient inflows, the situation has become self-sustaining. And there's enough in the way of sediment nutrient recycling to maintain hypoxia, to maintain conditions that are favorable for cyanobacteria, and to recycle nutrients at a rate that we're not going to break these feedback loops. So next thing we have to have a look at and understand is, in these conditions, how is it that cyanobacteria are able to exert dominance? And they use a whole lot of competitive advantages to do this. There's probably 20 different things we could go into. I'm just going to go into a couple of key ones. What's popped up on the left corner there is our normal algae. Cyanobacteria, firstly, very good research done by Cottingham and a few others on the ability of akinets to initiate nutrient recycling, and even in oligotrophic water bodies to have cyanobacteria dominance and cyanobacterial brooms. So the ability to mobilize sediments from mobilize nutrients from the sediments. And we're seeing that happening earlier and earlier in the year. And these akinets are able to sort of germinate February, March time and get a jump start on the competition. The other critical thing is the ability of cyanobacteria to control their buoyancy. Because nearer the surface, you'll see there's a little P popped up on the left-hand side there, where the oxygen in the water levels are higher, DO levels are higher, your phosphate levels will be lower. But obviously at the bottom, where it's anoxic, phosphorus levels will be higher. Similarly with nitrogen at the surface, probably going to be primarily nitrate. At the sediment, it's going to be ammonia. So why this is important is when the cyanobacteria are able to descend, they have access to a nutrient level and so nutrient abundance that your normal floating algae do not have. It's also metabolically more efficient to use ammonia as a source of nitrogen. And tests were done with radioisotopes to show that in conditions like this, microcystis are taking up 97% of their nitrogen in the form of ammonia. So they've got big competitive advantages to be able to go down at night, load up on nutrients, come up to the surface and bloom. Repeat that, and obviously you can rapidly get to a situation where the cyanobacteria have taken advantage of those conditions and exerted their dominance. So the next question is, what is it about treatments? We're talking about algicides here. Most people can understand fairly intuitively that if we apply herbicides, we're going to kill off biomass. It dies, decomposes, you've increased the sediment, you've increased the hypoxia and the oxygen depletion as it decomposes. Well, the same thing happens with algicides. When you kill off all the algae, you add to the sediment, as I said, as the cells drop to the bottom and decompose. But you've done so in an environment which is favorable to cyanobacteria. So they are the ones that bounce back more strongly, and you're playing into their hand with the use of algicides. So if we look into that a bit more deeply, the Government Accountability Office published their report 2.5 years ago on basically the failure of current management protocols to manage the risks around harmful algal blooms and hypoxia. And they made the point quite specifically that algicides kill the HAB cells, that can release the toxins, but also the decay in plant matter in the bottom is going to enhance hypoxia. So on top of that, there's long-established research that shows that copper sulfate or copper-based algicides are far more effective on beneficial algae than they are on cyanobacteria. So the effect basically is because the microcystis here has got a greater tolerance to copper sulfate, you are selecting for cyanobacteria by using it. Similar, another paper here indicating exactly the same thing, that the microcystis has a higher tolerance and therefore cyanobacteria can survive and even thrive at copper concentrations that are inhibitory to or lethal to green algae. This one, there's an interesting point 3 there, which I'm going to point out just now. Copper-resistant cells are significantly smaller than their non-resistant counterparts. So what we focus on is firstly looking at just the taxa. How many species are there? This is a project that we did where in 2021, algae sampling done from May through to September. On average, there were only 6 different taxa identified. And on average, 5.5 of those are cyanobacteria. So there is no competition to the cyanobacteria once a lake has got into this sort of condition. The other thing that we focus on a lot is bathymetry. And looking at, once we have that bathymetric data, we draw up tables like this, where we can see that at a depth of 32 feet, 30.7% of the surface area of sediment is hypoxic. And that means that 14% of the water is hypoxic. That is critical because that is the surface area of the sediment that is very actively recycling nutrients, and the volume of the water column that is denied to the animal life in the food web that's critical to keep it sustained. So in this lake, that gives you an idea of the proportion. That's a 30-foot contour. And this lake at the beginning of June became hypoxic at 32 feet. So that roughly shows you where it became hypoxic. What that translated into, as we say, is 14% of the water volume and 30% of the surface area was in a condition highly conducive to HABs. A month later, the lake became hypoxic at 16 feet. Now, you can see the significance of that. The surface area of sediment, which is anoxic, has doubled. The water volume, which is hypoxic, has tripled. So your conditions have shifted drastically in favor of cyanobacteria. They've now got conditions that favor their competitive advantages or them exerting their competitive advantages through a much bigger proportion of the lake. So we put that in there, it's 44% of the water volume, 61% of the surface area. If we look at the analysis of the phytoplankton, so the laboratory here reports it this way. This is non-toxin producing cyanobacteria, or BG, blue-green they call it. And this is HAB species. So we're purely looking at, and you'll see there that around about 40% of the cells are cyanobacteria, not toxin producing. About 5-6%, I think it is, are HABs. The interesting thing, you remember I referred in that one study that said copper-resistant cells are very small. So that's the cell concentration. 40% of the cells are blue-green, but a very much small percentage of the biovolume is made up of those cells. So 40% of the cells are making up only about 4% of the biovolume. In other words, those cells are very tiny. So we can see how it's very small cells that are resistant. Because when we came back a month later, that is what the profile had looked like. So we'd shifted from, and this is cyanobacterial succession. There's two ways they succeed. One is they succeed the beneficial algae by taking over. The other is they succeed one after the other. So what we'll find typically is early in the year, we'll see Ethanozomenon, Dolichospermum. As the year progresses, often you'll get the Warrencinias, the Plantothrix, and so on, and then eventually the Microcystis will show up. But this, by July, you can see what a shift had taken place in that we've shifted from non-toxin producers to toxin producers and got completely dominant. By the end of the year in September, we now have complete dominance here. The importance of this, why this is so important, is that this is a lake which for 4 years has been using more and more and more copper sulfate every year. And we said to them, this is what you need to be analyzing. All they were analyzing was chlorophyll A and showing that there's low chlorophyll A. Well, that can be for two reasons. One, you've killed off all the algae. Two, you've got cyanobacteria dominance. And so it was raised earlier, you should be measuring phycocyanin and not chlorophyll A. So basically what had happened in this lake, as they were using copper sulfate during this last summer, and all we've done is rework the data, but in essence, you started off with less than 50% was cyanobacteria, the majority of it non-toxin producing. By July, we'd had a switch to complete dominance by toxin producers. And by September, we've now got a big, big dominance. And if what you're measuring is chlorophyll A, you're probably going to register a reduction in chlorophyll A. And that's why that can so often be misleading. It was a good point that was raised earlier. So what's happened basically here, and this is not an isolated case, we've got a number of them, is the use of copper-based algicides has allowed the cyanobacteria to take over and dominate. So what can we do about it? Well, firstly, oxygenate. So here's data showing a lake which previously down at 5.5 meters became hypoxic. We oxygenate that. This is the same month, the year after we'd started a remediation program. We're oxygenated all the way down to the bottom. Significance of that, in 2021, the year before oxygenation was in place, we've got depth along the bottom. We've got DO on the vertical axis. At about 4.5, 5 meters, as you can see, became hypoxic. Once we've installed got the oxygenation going, we maintain oxygen all the way down to the bottom. Well, this is the correlation between your phosphates and ammonia, how when you had a hypoxic benthic environment, you had high nutrients, which, as we say, the cyanobacteria can access. And this is what it looks like when you're oxygenated. So you're able to suppress and manage the rate at which nutrients are reloaded. Important point to understand is aeration is not oxygenation. The two are not equivalent. And there's a lot of expensive mistakes made with that, not translatable technology. The second thing we do is bioaugmentation. And what we're talking about here is managing micronutrients, not adding bacteria, microbes, and so on. So two ways we need to measure this is one with looking at the taxa, and you'll see here, year by year, we've increased the biodiversity. We've created competition to the cyanobacteria. Next question is, well, how successful is that competition? And what this shows us is the total phytoplankton, of which something like 98% was HABs in May 2022. And you'll see over time how that has decreased to the point where midsummer this year, we had things completely under control there. So that really sums it up. Algicides are expedient short term, but they make the situation worse in the long term.
Thank you, David. There are a few questions.
Mm-hmm.
First by Becky. She offers, I'm curious about characterization of non-toxic cyanobacteria, given the growing number of potentially produced compounds that are not routinely analyzed. Was non-targeted analysis or a broader suite of potential toxin analytes considered?
We're actually in discussion with some of the labs because we would like to see the breakdown is there, but in terms of succession, as you get the succession from non-toxin producers to toxin producers, we think that distinction's relevant, but a total cyano is also a relevant parameter. So at the moment, we're kind of restricted to what is provided by the labs, but we are talking to the labs to try and get some variation and get a bit more granular on some of this data. Yeah.
Great. Now, Carrie asked this, as do I as well, because much of my work is pond management. And so, and I know there are a number of different systems available. Carrie asks specifically, how do you oxygenate the water?
Now it's probably not the time and place, but we have proprietary technology that we develop, we manufacture in-house and so on. It's scalable. We've done water bodies that are over 150 feet deep, 1,000 acres. And so, yeah, I don't want to get into big sales mode, but we have proprietary technology that's able to achieve it.
Just the very basics. Is it liquid?
No. It's superficially, it looks like an aeration system. So compressors on the shoreline, airlines run into radar units, diffusers. But what they avoid all the problems of conventional aeration, suspending sediments, oxygenating the upper portion and not the lower portion. And we actually are able to show that we have an aerobic benthic margin where the water and the sediment meet, and that is crucial to changing the microbiology at that benthic interface.
Personally, I'm curious about the hardware. I might drop you a line to follow. Is it a nanobubble thing?
No, not at all.
Okay, great. Well, I'm curious, and I might drop you a line just to satiate my own curiosity.
Sure.
John asks, can you say more about the difference between aeration and oxygenation? Why shouldn't sufficient aeration also work?
So the main problems are, one, typically aerators, and particularly aerators that have kind of been misappropriated from simple ponds, because they are turbulent and stir up the sediment, they're often set on stands and they sit 6 inches, 9 inches above the surface. Well, that means you're going to have that anoxic environment at the interface between the water and the sediment. The other is because they're purely dependent on transfer of oxygen from bubbles. The bubbles are smallest where it's deepest, so you're going to get minimal transfer there. The bubbles get bigger, but they shoot through the water so quickly that the time allowed for transfer is very small. But you run the risk and frequently lock in the phosphorus gradient, or, well, the dissolved oxygen gradient and the phosphorus gradient. So you reduce phosphorus levels at the surface, you don't reduce them at the bottom, so you still leave things open to cyanobacteria. And I'm going to make another point. Slip my mind. I'll add it in if I remember it.
Great, thanks. Brian asks, have you looked at zooplankton impacts from copper treatments?
No, we haven't looked at zooplankton from copper treatment. No, we do track zooplankton on some of our projects, and we see the improvements.
And this is my own personal curiosity, right? There are a number of different algicides available, and they're not all copper based.
Mhm.
Do you notice any, or have you even considered the difference between copper and, for example, those that create hydroxyl ions, right? The peroxide like
Peroxides and so on. Yeah, in principle, the fact that you're killing that biomass and sending it down to the bottom means they're the same. I have spoken to an academic who works for the World Health Organization on some projects in Brazil, who said that they believed they were seeing the same thing with the peroxides. So there were reservoirs there where they'd been using peroxides, and it had got to the point where it was not helping. The HABs are getting worse and worse. I don't know. I kind of wonder because, like you say, peroxide ion is so aggressive. You wonder how they would develop a resistance. But there's also been a lot of research done on the mucilage that microcystis and a lot of the other cyanobacteria produce in order to form their colonies. And there is a whole microbiome that exists in that mucilage. And there are some thoughts that the mucilage might be able to act as some sort of protection mechanism over time against the peroxides.
Yeah. And of course, one big difference is that copper has the potential to accumulate in sediments where the radical oxygens just don't.
Well, there was...
not as radicals, at least, right?
Yeah. There were some people that contacted us. They've been using copper sulfate for 15, 20 years. Got to the point where they wanted to physically dredge the lake because a lot of the coves had got to the point where people couldn't get the boats in and out. When they tested the sediment, they were told by the state agency that they would not be allowed to dredge it because there was so much heavy metals in the sediment that it couldn't be safely disposed of. And of course, the heavy metal was copper.
Well, this you've kind of answered peripheral questions, but there's a little bit of nuance here that might be useful. Renee asks, what does the process of oxygenation look like? But perhaps more importantly, in context, regarding what you haven't addressed yet, how could it be scaled up for larger bodies of water?
It's perfectly scalable. Like I said, we've done water bodies that are thousands of acres and over 150 feet deep. So, by area, by depth, by water volume, we're scalable. We've done quite a bit of work in drinking water reservoirs, and that's where we tend to deal with these bigger water bodies.
Upgrounds as well?
Sorry?
Upgrounds as well? Upground reservoirs, those that are built on top.
No. So big dams, dams, that type of reservoir, yeah.
Okay. And you've already addressed this question, but you said when you were last addressing it that you'd forgotten something, and I'm going to give you the opportunity to maybe remember if we're lucky. Grace asks, how do you oxygenate the lake, and what's the difference from aeration?
Okay, I know what the third one was. Often with your aeration systems, and this, as I understand it, was the case in that one where I told you they decided to scrap it because it made the situation worse. When you oxygenate and you create an aerobic benthic environment, your oxygen demand goes up because you still have that organic sediment, which is now decomposing aerobically. You have the benthic animal life, which is breathing oxygen, and you have more and more animal life coming. So you need to have the ability to deal with increased oxygen demand as the situation improves. And what often happens, it would appear with these aeration systems, is you get surges. They improve the oxygenation, so on. The oxygen demand goes up. The dissolved oxygen levels drop again because the system can't keep up with it. And again, there's been a lot of research that shows that cyanobacteria are far more agile and adaptable. And this is something that's come in, I noticed in the presentations earlier on Lake Erie. where if you look at on the stock market, they call it the VIX, the variability, but there's a lot of variability historically, say, looked like between about 1990 and 2010 sort of period. And in more recent years, it's stabilized at a higher level, the algae, the HAB levels. So the cyanobacteria are far more able to adapt to radical changes in the environment. And again, there's a lot of research about that around that. One interesting theory is that because they are prokaryotes and their genetic material is not sequestered in a nucleus, they are able to transfer and share genes. And so the genes that help adaptability are more easily transmitted and so on. But that is a problem. If the aeration system is not able to service the increased oxygen demand and you start introducing more variability into it, you are likely playing into the hands of the cyanobacteria, and that is why the situation gets worse, not better.
Great. Thank you again
And that
for your
was the
time,
point that I
David.
forgot. Thank you.
Sure. So there is one last question that was posted by Catherine that echoes mine about non-copper-based algicides, but I think we've already pretty well addressed that. And there are a couple more comments or general proposals actually in the Q&A session. And there are a couple of more questions that have materialized since. So including for Sony and David, some proposals by Ed, have a look. And if you care to type something in reply, please do. But also for David, there are a handful of questions that remain. But now we are breaking for lunch. So once again, thank you so much for your time. Thank you for all the participants. We will reconvene following lunch at 12:30 p.m. That's 1:30 Eastern time, of course, 12:30 Central. Thank you for all our presenters. It's been an excellent session. I've truly enjoyed, and I really appreciate your time given to us.